This is an exercise on dynamics, integrating the equation of motion of a physical pendulum. We call physical pendulum a rod or a mass that's oscillating versus the mathematical pendulum, where we have a string, massless string, with a lump mass at the end. So physical pendulum, like I said, it's a rod. We're assuming the length of the rod to be L and half a meter in length. The mass of the rod, 2 kilograms. In every dynamics book, you can find this equation that tells you what the mass moment inertia is of a rod of length L and mass M about one of its ends, slender homogeneous bar. We're going to assume various initial conditions. I have listed here 45 degrees, but we'll experiment with other values. And the pendulum starts from rest. I have here a figure. It shows a bearing at the end of a radius, and I'm listing here a moment of due to friction. We're actually going to assume friction to be negligible. So this is an undamped system, and that's oscillating freely, again, starting from rest in a displaced position off the equilibrium. Equilibrium is when the pendulum is aligned with the vertical. We have acceleration of gravity acting downwards. Okay. Equations of motion are easy to derive. This is a free body diagram, and we're going to sum moments about point O, again neglecting MF, that is friction moment. And for rotating bodies, we say, or we write sum of moments about adequate point. That could be either a fixed point, our case, or center mass. So you write equations of motion about this type of points, fixed points or about center mass. And what moments do act upon the pendulum is just the moment of the weight acting at the middle of the bar. So mass times acceleration of gravity. There is the downward force along the x-axis, the way you have it here, and the arm of the force is going to be half of length times sine of the angle theta. We measure angle theta, it's shown here, increases counterclockwise, and it's measured from the vertical, which is the x-axis. Okay, so sum of moments writes, assuming positive moment to be counterclockwise, and this is also the positive for theta for in its first and second time derivative. So positive theta counterclockwise, positive theta dot counterclockwise, positive theta dot counterclockwise. Okay, so the weight acting half of the or the middle of the bar is generating this moment. So I have the force times the arm of the force. Again, it's L over 2 times sine of theta, and this is equal to moment of inertia about point O times accelerating angular acceleration. And we explicit theta double dot second derivative of theta with respect to time. Integration will be with respect to theta, and this is how the equation of motion looks like. So negative mg times L over 2I sine of theta. In vibrations books, you're going to see consider the case of small oscillations, that is small angles theta, case in which Taylor series expansion allows us to replace sine of theta with the angle in radians. Anyway, so this is the equation of motion, and we're going to integrate it using Euler's method in Excel. Okay, so I copied, I'm pasting it here. We'll use it at some point. So let's see what the inputs are. I have mass, I have length of the pendulum, I have acceleration to gravity, and I have the calculated value will be moment of inertia about 0.0. Okay, so let's change this to times New Roman. And right, why is that? Because italic they look a little bit better. So I have the mass 2 kilograms in units here, kilogram. And then length, I said 0.5 meters, and then I have acceleration due to gravity 9.81 meters per second squared. Let me make this a little bigger. So I take S and going to font, I'm going to make it a superscript. This is okay. So, and then calculated. This is where an equation goes, and I have again for mass moment of inertia about one of the ends. It's calculated with the equation. The mass. Oh, I'm sorry. I want to do before that. I want to label. So you may want to pay attention here. Some of you may not know this. So I'm going to give names to some of the cells to make equation writing and debugging easier. So cell B3, which from where the mass giving the mass, some red are inputs. I'm going to call this M, and I wrote M here. Enter. Press the Enter key, and indeed now has the name M. For L, I'm going to just say L and enter, and this is going to be G. Okay, and then I have here there will be a value calculated using M and L, and I'm going to call this I. Okay, so I is going to be mass times L at power 2 over 3. Okay, so this is a calculated value, and units are kilogram meter square. And you copy this and paste. No, sorry. Copy and then paste. Sorry for this. So units are kilogram meters squared, and I'm going to elevate to make this again superscript just to look good. Oftentimes we're judged by appearance, not by content, but appearance matters. Make this kind of application more, or spreadsheet, more appealing. So I have the input values, I have the calculated moment of inertia, and now this will be the column for T. I can even say units, so it'll be seconds, and let's say, I don't know, maybe, or doesn't matter of aligning. So I center, but then move these back, justify right. And so again, this is the independent variable. 0 first row. The next one 0.002 and 0.004, 0.006, and this is enough for Excel to understand what I plan on doing. I'm going to expand it. Yes, so they recognize the pattern, and so it'll be like the first second and a read here, first second and a half of the integration. I can expand the column easily. Okay, and then I have the second derivative, time derivative of theta that will go here. I'm going to write it d. Theta is q as symbol. So there is I'm going to make this a square, and then dt squared, and several things, so font and superscript, and then this one also, it's a superscript, and then I'm going to select just q and turn it into a symbol. Alright, so I have d2 theta over dt squared, and this is going to be, so copy and paste, and paste again. Take the exponent, the squares off, and here I just keep q, or rather theta, and theta is going to be in so this is radians per second, rather radians per second squared. This is radians per second, this is radians, and I could add this, so squared, and make this yet another exponent. Alright, and here's a trick. I hold the Alt key and press enter, and now I have them as like broken on 2 rows, and then this one would be in radians per second, and likewise with Alt and enter, and this last one will be radians. Okay, of course I need to return to the times font, and it looks like the boldface. Okay, let's make it just 10. All right, so this is the header. I said initial conditions now. So at t equals 0, the time derivative, the angular velocity of the rod is 0, and then so let me format just a little bit. So let me format this. This is going to be format cells, and I have number, and let's go with 4 decimals. I'm going back because I want to do another thing, to also center them. So again, format cell number, number will be 4 decimals, and these will be, I make them red color because they are input. An initial condition for position, we set 45 degrees, so this is 45 times pi, pay attention here, open close parentheses, over 180. So this is the value in radians for 45 degrees. Okay, so this is the column for, again, we're doing Euler integration, and if you go to appendix to useful formulae, integration first order ordinary differential equations, ours is second order, so we need to do it twice. But really what this Euler method is, you move along the slope a small amount from current time to the next time step, or this is a time step to the next time discrete value of time, and then you repeat it, so you move along the tangent repeatedly, and you approximate the function that you're y of t that you're interested in. So the I'm sorry, need to go back to the should have used this. So the integration step is the one that you're seeing here. Next value is previous value times the derivative and times the time step. So press the print screen, go to Paint, and I'm going to just copy this and have it as a reference. So this will go into the spreadsheet. I have the formula, equation of motion, and then this is the integration step, so that I can look at them as I'm writing the spreadsheet. Okay. So first value, I'm going to program this equation again. So it's negative. I have m times acceleration to gravity times L over I, and then instead of divided by 2, I'm just saying times 0.5. Okay, and then times it's going to be sine of theta, and close parentheses. Before moving forward, since we may use these named cells, let's go to this tool, Name Manager. So I clicked on Formulas in Name Manager, and you have them here. So there's G, there's I, there's L, a little bit of a confusion there, and then there's M. All right, you can edit, you can change their values. You can have a cell named with multiple names, that is aliases. Okay, so and I'm going to expand this. Of course, this is referring cells that have not been populated yet. So this is f of t column, and then this is going to be y. I have y at k, in particular k here is 1, and the next value is going to be of y is going to be previous value. Again, I'm coding now this equation. So so previous value plus previous f value, and is this one, times the time step. And I'm going to just say, open parentheses, this value, negative previous value, and this is it. So I have, and now the equation is going to, repeat itself with, so for k plus 1, I have k plus 1 of time, and k of time. And then I need to do the same. So apply the Euler step for theta. So like I said, being second order differential equation, I need to apply Euler step twice. So here I am, the second value is going to be previous value plus the function f, the slope at k, which is previous value, times, and again it's going to be the time step, this value, negative this value, and I close parentheses. Okay. So yeah, this is it. I have the time variable, and I have the and I have theta. So I can plot theta as function of time. That's called the time response. I can of course plot the other two. Let me select these first two cell columns, and I'm just going to plot a graph of them. So insert and charts, and it will be all charts, and scattered in this one, no markers and no smoothing. Okay, so I have the the acceleration. If I want the, and could change it to where I have more. Let me do this. Let's add some more value. So I have, let's go all the way to 1,000 values, or past 1,000. So something that's easy to remember. 1,200. Okay, and then no, that's not what I wanted to do. I wanted to zoom out, and then this one all the way down, and this one all the way down, and let's see, format, select data, and data was 6 instead of 6 3 whatever one, I put 1 2 1 2 3 zeros. Okay. Oh, it stopped. Okay. Didn't want to. So what I need to do is to go where the graph, the values, and expand them all the way down. All right. So now I have multiple oscillations, actually 2. Okay. And this may look like a sine wave. It's only 45 degrees. We can play scenarios. I have an interest in, although I have an interest in the displacement rather than acceleration. And this was symbol. And then I can, like I said, I can play scenarios. So if we change the initial condition from 45 degrees to 90 degrees, like you start the bar horizontally and let it oscillate, is the appearance of the graph. But now if I change it, for example, it starts from 120, and oh, these are okay, 120 pi 25 times pi over 180. Well, the problem was stated, integrate from 45 degrees. All right, so this is the shape of the graph, and I hope I haven't missed anything. Let's say if I look at this graph, it's also harmonic function. Acceleration is a quasi-harmonic. Again, for large oscillations, they're not going to be a strictly harmonic response. But this is pretty much what the intent was, to show you how to use Euler integration, drive the equation of motion for a physical pendulum, no damping, and integrate and excel using Euler's method. So let me double check. I have Okay, so everything appears to be fine. I'm going to share on Blackboard, post on Blackboard this this document as well as the spreadsheet, and this is it. So I'm stopping recording.